project for intermediate heat transfer class. So throughout the course, we have been quite familiar with the concept of convective heat transfer and conductive heat transfer. So this simulation will focus on these two concepts. This is try to simulate the case when the submarines travel across oceans that they will experience very extreme temperature conditions on the outer surface. They will experience some heat loss due to convective heat transfer on the outer surface, and some heat loss due to the conductive as well. So the goal for the problem is we would embed an uniform volumetric heat generation within the wall so that it can keep the temperature in the cabin stay constant at room temperature. I've developed an ease model to simulate the temperature distribution and the required heat generation within the wall, and we will have a look at that within just a couple minutes. So to make the problem feasible, we can make a couple assumptions. We can assume that we have uniform heat volumetric heat generation, uniform thermal properties within the plate and within the flow. Flat plate, so the flow will start with laminar flow conditions, non-compression flows, and no radiation heat transfer. So we will mainly focus on conduction and convection heat transfer. So on the top right here is where I set up the properties for the long plate of steel. So our simulation is going to be a very simple version of submarines, which is we have several flow conditions on the top surface of a flat plate with several different lengths. So the reason why I let the flow condition to be variable, because we will want to study the effect of convection as well as conduction. Oh, I'm so sorry. We want to study the effect of laminar as well as the turbulent flow, so we can have a very clear insight of the external flow problems. So over here is the thermal properties that we will be used to solve our problems. We have the free stream velocity, free stream temperature. We have several lengths of the flat plate. So in our simulation, we will use oil, water, and honey as 3 different flow conditions. So the procedure is step 1 to find Reynolds and Prandtl numbers. Step 2 is to find the heat transfer coefficient from the Reynolds and Prandtl number that we found in step 1. Step 3 is actually optional. I want to have a look at the temperature distribution within the flat plate. And step 4 is the most important one, where we want to compute the heat generation by using the conservation of energy. So let's have a look at the ease model. on the slide right here, I'm sorry, on the slide right here, I have set up the properties inputs of the plates and the flows. So as you can see, right here we have some very nice properties for the plate and for the different flows, oil, water, and honey. So this one is a computation over the first plate length, which is 0.1 meter. We have some calculation of Reynolds number, and from that we can calculate Nozet number. Since all the Reynolds number were since all the flow condition was laminar, we can use this equation right here to calculate the Nozet number. So from the Nozet numbers, we can have the convective heat transfer coefficient, and from that we can find the convection heat loss to several different flow of oil, water, and honey. Right here is where I calculate the conduction heat loss by using just the equation in conduction chapter. So by using the conservation of energy, we can find that the required heat generated equals to the heat loss due to convection plus heat loss due to conduction. This in the second configuration is exactly same as the first one. We have all three flow conditions end up to be laminar flow. And the last one is something, the last one is something that turbulent happen in water and oil flow. So we will see different effects on this one. This is the result table. As we have expected, when we have the honey flow right here, the heat required to be generated is the lowest, and when we have the water flow, the heat required to be generated is the highest. So right here is like almost twice as much as the heat required over the honey flow. So I have developed MATLAB model, the visualized model of the required generate heat versus flow conditions. As you can see, the green line on top is the water flow with the highest required heat, and on the bottom is the honey flow with the lowest required heat. And right here is a temperature distribution within the 5 meters long plate. So for the 0.1 meters and for the 1 meters, they look pretty much the same. So I decide to have this one as a representation only. Thank you for watching my presentation.